Hello, everyone. This is Jingfeng, a researcher in Recon AIT. Today, we are really happy to have our speaker, Teresa from IFO, to give us her talk, Robustness while Cross-Domain Ensembles. Teresa is a PhD student at IFO, and she received her bachelor and master degree from NUS and Cambridge, respectively. Her interest is in building robust and adaptive computer vision models. Teresa, please get started.
Okay, thanks for the introduction. So most of this talk will be on our paper, Robustness by Cross-Domain Ensembles. And at the end, I will give an overview of the projects that we have been working on in the past year. So this paper, Cross-Domain Ensembles, is joint work with Osan, Sasha, and Amir, and it was presented at ICCP 21. So neural networks in the real world will encounter data with distortions, such as defocus blur, JPEG compression, or adversarial shifts. So here is an example. So the first column here shows a clean, undistorted image and its corresponding surface normals prediction from a standard network. So these predictions tells us about the surface orientation of the objects in the image. Most of the visuals in this presentation are on this task. The same trend holds for the other task, and I will show their results in the experiment section. So the next two columns shows the clean image under slight distortions. And the bottom row again shows the corresponding predictions. So the ground truth is shown in the bottom right. And as we can see, small and non-adversarial image distortions can cause large errors in the network's predictions. And as expected, the error in these predictions gets worse as the distortion intensity increases. So we can see this in the plot on the top right. So this is a challenge that needs to be solved for models to be useful in the real world. And this is the focus of this paper. So our proposed method is based on ensembles. The core idea behind ensembles is relying on the diversity of individual models to decorrelate errors. Sources of diversity include using different initializations, like deep ensembles, different hyperparameters, network architectures, or by modifying the training loss. So instead of using different hyperparameters or architectures, our ensemble makes predictions from a diverse set of cues that we call middle domains. And we merge the predictions from these middle domains based on their uncertainties. So this is an example of how our method works on a single image. Given a distorted input image where the distortion is JPEG compression, we extract a set of middle domains. Examples of these middle domains are 2D edges, low-pass filtering, grayscale, and emboss filtering. So note that these middle domains can be computed analytically, so they do not need labels, and they can be obtained for any dataset without supervision. So given the middle domains as inputs, we train a network to predict the final target domain, which in this case is surface normals. So each middle domain and its corresponding prediction defines a path. So as we can see, each path reacts differently to this distribution shift. So the prediction quality differs among paths. So in this case, the low-pass filter path, shown in the red box, does not degrade as much as the others. So to obtain uncertainties, we model the network output as a Laplacian distribution with parameters mean and sigma. So mean is the prediction and sigma is the corresponding uncertainty. The uncertainties are colorful because the surface normals is represented by 3 channels. So its uncertainty is also represented by 3 channels. The darker the uncertainty, the more confident the network is about its prediction. So for each path, we train a network with a likelihood loss. So we now have the predictions and uncertainties for several paths. To merge these predictions, we first convert the uncertainties to merging weights by taking the inverse of each path's uncertainty. And the idea is that each path will contribute to the final prediction based on its uncertainty. So for example, this path has degraded prediction, thus high uncertainty, which results in low merging weights compared to the other paths. So we merge the predictions from different paths by using the merging weights and to get our final prediction. So we have seen an example with a single image. We will see now how this works on a short YouTube video. So our ensemble has 8 middle domains, resulting in 8 paths or 8 networks. These are their predictions, corresponding uncertainties, and weights. The final prediction is shown in the top row, and see how each path's prediction differs. So for example, the low-pass path has lower uncertainties with more accurate predictions on the floor. So this is also reflected in the higher weights. So remember that we model our output as a Laplacian with parameters mean and sigma, where the mean corresponds to the prediction and sigma is the uncertainty. So as shown in the video, our method relies on the uncertainty estimates to merge predictions. However, we know that uncertainties can be miscalibrated under distribution shifts. So this means that there is a tendency to output poor predictions with high confidence. So to calibrate the uncertainties, we propose an additional training stage that we call sigma training. So in the first stage, we train a network with likelihood loss to predict mean and sigma. And in this additional stage, we feed the network with out-of-distribution inputs. So we train with 2 loss terms in this stage. The first term helps sigma to increase when faced with out-of-distribution data, and the second term helps to keep predictions fixed. So this is an example of overconfident and incorrect predictions. The image has been distorted. This image has been distorted with 2 different levels of speckle noise. And these are reshaped predictions from a single path. So these predictions tells us about the illumination of the scene. Before sigma training, when the model produces poor results, the uncertainty does not increase correspondingly. So we compared this to deep ensembles, which has also been used to get uncertainty estimates under distribution shifts by taking the variance of different predictions. So we can see that it is also overconfident. So after sigma training, the uncertainty estimates are better calibrated to account for degraded predictions. Because we have a term in the sigma training stage that keeps predictions the same, our predictions did not change. So if we compare the predictions before and after sigma training, they are the same, but the uncertainties are higher. So in this example, sigma training has successfully calibrated the uncertainties. So we quantify this with a scatter plot here. It shows the error against average sigma. Each point is an average over 16,000 test images for 1 unseen distortion and 1 severity level. So before sigma training, as shown in the green dots, the sigmas do not increase with an increase in error. And this is the same for deep ensembles, which is shown in blue. So after sigma training, there is a stronger correlation between uncertainties and error, and this is shown in red. So to summarize, there are 2 key elements of our method. So first, we have a diverse set of middle domains, so it's likely that one of them will be less affected by distortions and returns an accurate prediction. And the second, as we have just seen, that the errors of the prediction correlates well with its corresponding uncertainty estimates. So this means that the uncertainty is low in the regions of the image where the prediction is accurate. And so this allows us to use the uncertainty estimates as a signal to have a final prediction where parts of the image is taken from different paths. So now let's look at some results. So this is a summary. We obtained improvements in robustness compared to several baselines under non-adversarial shifts and adversarial ones. for several tasks and data sets, like regression on taxonomy, replica and the habitat dataset, and classification on ImageNet and CFAR. So let's start with some qualitative results. Each row shows an image from the taxonomy test set under increasing speckle noise. So this is the predictions for the surface normal stars and the corresponding ground truth for comparison. So our method degrades less than deep ensembles, which is shown in the second last column, and using a single model shown in the last column. So this difference is more obvious at higher distortion intensities, which is in the last row. So finally, for depth estimation, we see a similar trend. So this demonstrates the effectiveness of using different middle domains to obtain a robust prediction. So we have more qualitative results under 4 different distortions: impulse noise, defocus, blur, contrast, and pixelate. On the sample image from the replica test set, so each prediction is followed by its corresponding error map. So for pixelate here, the improvement over ensembles and using a single model is clearer. For the other distortions, we circled the improvements in fine-grained details. So these are more qualitative results on a YouTube video. So this video has been corrupted by increasing shot noise. So our method returns more accurate predictions with less flickering. So now we can look at some quantitative results. So these are the results for common corruption distortions applied on the taxonomy test set for surface normals prediction. Each point shows the error average over 11 unseen distortions, and these are L1 errors, so the lower it is, the better it is. So some of the baselines worth mentioning. Yellow is a single model that goes from RGB to the target task. Dark blue is deep ensembles. Light blue and dark brown are single models, but with data augmentation. So where light blue is adversarial training and dark brown is with style data. Red is our method, which clearly outperforms the baselines. Purple and green are variants of our method. So the purple variant uses a network to do the merging. So it takes the predictions and uncertainties from all paths, and in the end returns one final prediction. So merging with the inverse variants has similar performance, and it has the advantage of not needing to train a network. It can work with arbitrary number of paths. It is also interpretable. So green is a simple average from the different middle domains path. And note that this simple average variant can be most of the baselines. So, but merging the predictions using uncertainties can give a further boost in performance. So the trends are similar for depth and reshade task. Deep ensembles have a similar performance compared to using a single model, even though augmentation methods such as adversarial training and style are competitive baselines. So our method has a stronger performance compared to them. We also have quantitative results for the same task on other datasets such as replica, habitat, and the supplementary material. We also quantify the adversarial robustness of our method under different attack strengths. So these are L1 errors. Our method used lower errors compared to the baselines. And we think that this is because using middle domains promotes ensemble diversity in a way that makes it more challenging to create an attack that fools all paths simultaneously. So here is a video showing an image that has been corrupted by increasing attack strength. So our method returns more accurate predictions compared to the baselines, for example, in the circle regions here. So we can also look at the epistemic uncertainty. It is used to represent the uncertainty in the model parameters, and it's computed by taking the variance across the different predictions. So this is different from the predicted uncertainties from a single model that we use for merging. So we can compute this also for deep ensembles. The plot here shows the L1 error versus the epistemic uncertainty of our method versus deep ensembles. And this is computed over unseen distortions. So our method has a stronger correlation of uncertainty with error, and thus a better indication of distribution shift. So we can see an example of this with an image that has been corrupted by increasing pixelation. So we have seen how the predictions changes. So both deep ensemble and our method will be affected by distortion, but our method is more robust. And here we can also see how the epistemic uncertainty changes. So ensemble returns higher uncertainties under high distortions, while deep ensembles can output poor predictions with low uncertainties. So our method is not limited to pixel-wise regression tasks. We show the results here for ImageNet classification under clean and distorted data. The second column here is the error for clean data. We also show the individual errors for each distortion from the different categories. And the average column in the third column is the average of all these numbers. So our ensemble predictions for classification are a simple average of the predictions from all paths. So the only difference between deep ensembles and our method is in the use of middle domains. We also have supportive results on CIFAR 100 in the supplementary material. So now we can look at some ablation studies. So this one looks at the effect of increasing the number of paths and the role of uncertainty when used for merging on the final performance. This plot shows the L1 errors on out of distribution data. Each point shows the average error over all possible combinations of paths for a fixed number of paths. So for any given number of paths, our method in red consistently outperforms deep ensembles, which is shown in blue. This also implies that performance is not sensitive to the choice of middle domains. And we can also see that the performance gap increases with more paths. So a variant of our method, uniform merging, which is shown in green, it does a simple average of the predictions. It also outperforms deep ensembles for all number of paths. And again, we see that merging uncertainties for the boost performance. So this has a steep downward trend, even at 8 paths, but we did not experiment with more than 8 paths. So this is another ablation study to analyze the importance of each middle domain. This chart has 11 axes. Each one represents one distortion. So we will look at the path from the 2D edge middle domain first. So a curve will get 1 on the distortion. It contributes the least to the performance, final performance, and contributes an 8 when it contributes the most. So here the 2D edges path is helpful for shot noise, pixelate, and less helpful for color distortions, for example, brightness or saturate. Probably because edges cannot be computed accurately on these distortions, so the predictions from edges is poor. So this is the rest of the paths. So there are 8 middle domain prediction paths, so there are 8 curves here. We see that the low pass middle domain was most helpful for noise distortions. The sharpen domain was most helpful for contrast distortions. This plot also tells us that different paths react differently to different distortions, and the overall performance is not attributed to one or a few middle domains. So we have more ablation studies and results in the main paper and also in the supplementary material. So to summarize, this project using middle domains promotes ensemble diversity, which improves performance by decorrelating errors. And it has a negligible increase in computational costs compared to deep ensembles. Uncertainty-based merging allows the method to select regions from the best performing path. We obtain improvements in robustness compared to baselines under distribution shifts, such as common corruptions or adversarial attacks for both classification and pixel-wise regression tasks. This improvement in robustness did not come at the expense of the performance of in-distribution data. So this is an overview of cross-domain ensembles. So now I will move on to two other projects that we have been working on. So the first one is 3D common corruptions that Osan has presented last week. So here, to compute these corruptions, these 3D corruptions, we use transformations that incorporate scene geometry. And as a result, we have corruptions that are more realistic and more likely to occur in the real world. So for example, motion blur shown in the first column has a motion parallax effect, where objects further from the scene is sharper, and this is compared to the common corruption benchmark. It's shown in the second row, where blur is applied uniformly. So another example is the object occlusion in the last column, where we change the camera position such that the plant increasingly occludes the fridge. Right, so the unoccluded parts of the fridge is shown in blue, and the occluded parts are shown in red. So in the 2D case, random patches are dropped, which is less realistic. So for 3D common corruptions, we introduced about 30 diverse corruptions and showed that this results in a challenging benchmark. We applied this on Taskonomy dataset and also on ImageNet and COCO. And we showed that training with these corruptions improves robustness. And we have a demo where you can upload your own image and compare the predictions from our models against the baseline. So you can check the paper or website for more details. So the last two methods, cross-domain ensembles, 3DCC, they're about training time robustness mechanisms. So they try to some extent anticipate the shift that will occur and incorporate these mechanisms at training time. And at test time, these models are frozen. So we represented this with the diagram on the top. So F theta is a network that predicts, in this example, depth from a given image. So, but we know that distribution shifts are numerous and unpredictable. So this project is about equipping models with the ability to adapt in test time in a way that's fast and reliable. So this is currently under review, but I will give a high-level overview. So a popular way to do adaptation is by optimizing a proxy quantity at test time. This is a quantity that can be computed at test time. So for example, uncertainty or self-supervised tasks like rotation prediction. So these methods optimize this proxy quantity with the hopes that it will improve predictions on the target task. But optimization can be slow, unstable, because we may need to tune the hyperparameters of the optimizer. So our method is shown in the bottom diagram. It extracts an adaptation signal and uses a side network to do the adaptation. So we showed that it works well on out-of-distribution inputs, and because we only need to do a forward pass at test time, it is orders of magnitude faster than optimization approaches. So we will be wrapping this project up, and we will have the paper on arXiv soon, so stay tuned. So I guess that's all for my presentation. Thanks for listening, and visit our website crossdomainensembles.epfl.ch for more information.
Great. Thank you very much, Teresa, for this great talk. I think we had a few questions during the talk. So I suggest that we go through them first, and anyone, if you have any questions, you can just ask them or put them on the chat and then I will read them. We got two questions from François Béranger. I don't know if you want to tell them yourself or I can.
Yeah,
can read.
I can read. The prediction is edge orientation. I guess. The prediction. So in the prediction column, that task is surface normals. The middle domain is edge orientation, is edges. So edges, like 2D edges, can be extracted from the RGB analytically. It's just taking the gradients in the X and Y direction. So it can be computed on any image. So we first, given an RGB image, we extract this 2D edges. So that will be the second column, first example. And then from there, we train a network to predict surface normals. So I guess your next question is, how do you know the surface normals of the scene? So we use this data set, taskonomy, and it has about 20 different tasks. It has 4 million images and many tasks, and one of them is surface normals. So we are training the networks with this data set.
Great, thanks. Anyone else? I do have some questions as well. Just to better understand for the Sigma training, you mentioned that you optimize the weights of each middle domain. And I was wondering if you can elaborate more about this process, because I feel that it's really critical to, because later on you demonstrate that each middle domain has different contribution depending on the target task. So how do you ensure the right weights during the Sigma training?
Yeah. So it's basically so in the first stage is a standard likelihood loss training, and in the second stage we just in the addition to this likelihood loss, just to because we just continue with training, we added 2 additional terms. So it's these 2 terms that you see here. One is sigma calibration and one is mean grounding. Right. So the mean grounding basically keeps prediction fixed, and the sigma calibration gets the predicted uncertainties to increase. It's something like an L1 loss that is computed against for example, the error. So it's trained to increase under out of distribution inputs.
Okay, I see. We have new questions from François Béranger. It's more about how we can generalize this concept to non-computer vision datasets.
That is a good question. So the idea is basically that we try to from some given input, we try to extract some kind of analytical. We compute some kind of analytical like middle domains that we know will be robust to different things. And then at the end, combine the predictions from these middle domains using uncertainties. So this is the high level idea. We only show this for vision datasets because we are like, we mostly work on computer vision. But this idea of first extracting middle domains, like forcing the model to go through these kind of like classical features, because they are robust to different kind of shifts, and because they are also interpretable. I think this idea can be applied for different kinds of modalities.
It brings me to a follow-up question to François' question. the thing is, if we want to implement it in the real world, do you feel that the fact that we are using this middle domain has computational overhead that is significant, or we can deploy them for real-time computer vision?
So these middle domains, like for example, 2D edges, it's just two convolution filters. Like it's just computing the gradients in the X and Y direction. So the increase in cost just from computing a middle domain is almost negligible. So like from RGB to middle domains, they are not a network. They are like simple classical feature extractions. So
Okay,
there is negligible, increase in computation.
Okay, nice. Thanks. If no one has any more questions, we can wrap this session. And thanks again, Teresa, for her talk and the work of her team. Thank you very much. And thank you also for people who joined.